Alright, so what I'm going to do here, I'm going to erase this. We're going to look at an idea about how we measure things. And one of the things, being a scientist coming to statistics, doing physics and astronomy, is that if we measure something, we never really truly have a perfect measurement. Right? Whatever your ruler is, you have markers. And the things you measure don't always line up exactly with your markers on the ruler. And so you have to estimate. Usually you can estimate the halfway point. So if this was like 1, 2, 3, I could say, well, that's at least 2.5. Maybe if it's visual enough, I could say, oh, that's probably 2.6. But it's a guess. And so we have to have some way of letting people know when we communicate how good our measurement is. And that's one part of the problem with measurement. The other part, right, like, let's say we have a flagpole. And I want to say the flagpole has a definite height. Well, each side is not perfectly the same, right? They're close, but they're not exactly the same. And it's made up of atoms connected together that are bouncing up and down all the time. So literally, the physical reality of an object that isn't at absolute zero, isn't, negative 273 degrees Celsius, is that the length changes constantly. And we can say this about anything we measure, that there's no true measurement. And at some level, we're estimating. I could get a laser that has a wavelength of light on it, and the best I could measure is whatever the width of that wavelength of light is, plus how it's bouncing up and down. And so part of the idea of statistics being how we observe, or the science of observing, is we talk about measurements differently. We talk about measurements being average values, and there's some spread or error in a measurement. Error isn't inherently wrong. It's just the nature of how we have to observe reality. The definition of a perfect measurement isn't true. And so in statistics, we learn to take care of that. Now, there are some things, counting things, that we can get good measurements on. But when we measure some real number, let's say I measure my height in meters to be 1.73 meters, we have to talk about how we estimate it. I didn't do any of the decimal places after. What we do is we say significant figures. And we list in significant figures the things we know for sure looking at the ruler, and the last thing we have to estimate. So for here, I knew for sure this was 2. But I had to guess the halfway point. Or if it's big, if the space is big enough that you can see well, I guessed at the 0.6. And so I have 2 figures here, and so this is 2 significant figures, 2 sig figs. That's what we say. Here, when I guess my height or measure my height, the 1.73, this has 3 significant figures. And what I'm saying is, of my measurement, 3 things are significant. Because if I say 1.73 meters, that's one thing. But I could say 1,730 millimeters. And the question becomes, does this 0 matter? Well, if I look at the significant figures, what I'm saying is my measurement is good here. And these units are the same thing, meters and millimeters. And so we explain how well our measurement is by listing the significant figures. And the thing we tend to do when we do our calculations is we round to how many significant figures we need. And we'll learn some rules for adding, subtracting, and multiplying significant figures. So let's say I have 2 things I've measured. I'll go back to the example I was doing before where I wanted to measure the area of a rug. And I'll say that I measured this to be 3.2 feet. Because it was long, I had to use a tape measure that wasn't as accurate. But down here, I measured this to be 1.01 feet, right? Because I had a smaller This is a rug, it's more like a towel, right? Sorry. Because I had a smaller device, it had more tick marks on it, and so I could estimate a little bit further than I could here. And so to find the area, I want to multiply the length by width. So I'll come in and I'll multiply 3.2 feet times 1.01 feet. And the nice thing for me here is I always use my calculator with decimals if I can. It saves me from doing long multiplication. Let's see, 3.2 times 1.01 is, let's see, 3.232 feet squared, because that's what we'll report area. But we have to talk about significant figures, because this is an estimate. The estimates I've put in here come and affect my answer. And so the rule we have is we look at the significant figures on both of my measures. This has 3 sig figs, and this has 2 sig figs. So 3 sig figs and 2 sig figs. And when I multiply and divide, I use the smallest sig figs, the smallest amount of sig figs. So in this case it was 2 significant figures. And so I come back here and I have to round this to 2 significant figures. And so the 2 significant figures are going to be the first 2 here, the larger numbers. And so this is 3.2, and when I round, I look to the thing to the right of the number I'm rounding to. Now this is less than 5, so I truncate it. It doesn't matter, it's not significant. And now I have 3.2 feet squared, and this is to 2 sig figs. All right, let's do the same calculation, but up top, I'm going to have 3.481 inches. And on the side, I'm going to have 2.1 inches. And so I'm going to multiply to get an area. 3.481 times 2.1. So 3.481 times 2.1 gives me 7.3101 inches squared. Now I look at my sig figs. Whoops, that's for another problem. This has 4 significant figures, and this has 2 sig figs. So again, even though I got more accurate on my length here, I'm still stuck with 2 sig figs here on my width, and so I can only give 2 significant figures on my answer. And so that's 7.3 inches squared. Now, using and reporting sig figs, when we go to add, let's say I have 3.8417 feet, and I add to it 3.1 feet. Now notice the precision, or how precise my measurement in comes into play, because what's going to happen is when I go to add these, I'm going to line them up like we would be adding up and down. And notice what happens here. I had to guess, right? When I do sig figs, I guessed at this number. So there could actually be stuff over here, but I didn't have a ruler that could measure that far down. And so this is a guess. Well, if this is a guess, none of that's going to be significant. So I added up 7149.3, but I have to keep the decimal place that's furthest to the left here. And so all of that stuff gets lost in me guessing on this measurement. And so we add, when we add or subtract, we round to the largest, how do I say it? It's the least precise. So for example, I lost the word for it. It's to the left on my number, in magnitude, and it's the smaller precision here. So if I have 3.9 and I add to it 0.00000001, so I add all this stuff up, 3.900000001, well, this was my most significant thing, or my least precise thing. And so that's the only decimal place I can keep. And it's kind of saying, if you measure something so small, it doesn't really change what you can measure with this ruler. And if I come back with this ruler that I measured this with, I'm not going to see that bit that I added. And so we keep the least precise. And precision tells you where you are around the decimal place. And so when we add and subtract, we keep the least precise. And the other thing we have to do is look at, this all depends on rounding. And rounding is based off of the number to the right. So I'm just going to make a big number here, and I'm going to round to different places in it. So let's say I want to round to the first decimal place. This is all I want to keep. And so what I'm going to do is I'm going to look to the right. And if the number to the right is bigger than 5, I increase this by 1. So 3.9 is bigger than 5, so I make it 3.9. Alright, I'm going to change colors here. And let's say I want to round to this decimal place. So I look to the right, and I go, is this number bigger than 5? Sorry, my dog wants out. I'll be done in a second. And so it's not bigger than 5, so I drop it. And so that leaves me at 3.8970. And I need to keep the 0, because it's holding the place of where I rounded to. And that's the basic of significant figures and how we can talk about how well we can measure when we report a number. And my apologies, I'm going to go let the dog outside.